Welcome to Nonlinear Optics. I'm again here alone for the first time in Nonlinear Optics actually. I hope the technology works and that you can hear and see me. What did we do in the last lecture? Let me do a quick review. As I said, it was one of the most important lectures in this course, namely the derivation of the coupled wave equations. The coupled wave equations describe how the waves that are involved in the nonlinear interaction, how they develop as they propagate, say, through a nonlinear crystal. And we did this for the example of some frequency generation. And what we derived were three equations, because in some frequency generation, if we speak about a second order process, then we have three colors that interact. All right, so we had written down these three equations here, and I just copy them in a little bit nicer form from my script. So, and you see that, well, if we speak about some frequency generation, then the input fields may be A1 and A2, and what is created then is the sum frequency A3. And what we have here, once again, is the amplitude, the complex amplitude. And what we see is how they grow or actually get smaller. This can also be the case, of course. So we see how they grow within a crystal. So let me make a little sketch here. So suppose we have here a nonlinear crystal, and we have here the wave A1 and A2. Right? Then typically in some frequency generation, the wave A3 will be zero still here. Right? So the amplitude A3 will be zero, but what we do expect for this amplitude A3 is that it will grow. Right? And the question is, will it grow forever? How will it grow? Linearly, quadratically, something? But it may also be the case, and we'll see this today, that it goes down again. Why? Well, because these three colors, they may get out of step, they may get out of phase, and then this energy transfer from A1 and A2 to A3 may be reversed, such that actually A3 delivers energy to A1 or A2. So this is what we derived for some frequency generation. For the other nonlinear effects that we discussed already, there will be different coupled wave equations. And certainly we'll ask you in some homework problem to derive for another process the coupled wave equations. And in the next chapter, actually, we will derive the set of coupled wave equations for second harmonic generation. The next thing that we did with these coupled wave equations was to find some solutions. And of course, we would start with the easy, if not to say the trivial solutions. And actually, the one with which we started under the headline, phase mismatch considerations. So you see that this subchapter has actually two purposes, namely, in the first instance, we find simple solutions to the coupled wave equations, and in the second instance, we learn at the same time, and this is what will happen in the next few minutes, we will learn something about, well, the typical properties of phase matching, or of phase mismatching, actually. Okay, so what we did last time was to assume that A1 and A2, so these two input fields here, that they are very strong, and this field A3 is very weak, and therefore we can assume that these two here don't change along this coordinate z. Yeah? And if this is the case, if A1 and A2, if they don't depend on Z, right, then here in this formula we have a constant here and here, and then this differential equation is fairly simple. They are no longer coupled. And we made it even simpler because we assumed in the first step that delta k, that this phase mismatch is also equal to 0, so that we have perfect phase matching all the time. We didn't say how to realize that, how to achieve that, but we simply assumed that it's 0, and we found, of course, a very simple solution, namely that the amplitude A3 will increase linearly with the propagation distance here. And this means that the intensity increases quadratically, right? Okay, now we will drop this simplification that delta k is equal to 0. So the situation that we will have is not quite as trivial as it used to be. So let's start with this. We consider the more general case. We now consider the more general case namely that delta k is not equal to 0, right? And what we want to know is how big A3, how big the amplitude is after some propagation distance of z equals, say, capital L. Well, where L could be the length of the crystal or something. Yeah? So we want to calculate A3 after some propagation distance z is equal to L. And this means that we need to compute A3 if z equal to L. And the only thing that we need to do is, of course, to integrate this equation 30c. Yeah? Okay, so we just write it down. So we have the imaginary unit 2 times the nonlinear susceptibility, yeah? Basically. So we call it the effective nonlinearity. There will be a chapter on that later. And here we have these two amplitudes. I said we integrate, but we know that A1 and A2 are constant, and therefore we can write them outside the integral. But now the integral comes, so we integrate from z equal to 0 to z equal to L, and what is in the integral is, of course, only the exponential I delta k times z, right? And this can be integrated immediately. So we have to copy these prefactors. K3 times c squared A1 times A2. And now if we integrate that, then we get e to the I delta k times L minus 1 divided by I times delta k. Yeah? That's equation 31. And now we want to look what this equation 31, what does it say to us? And well, the first thing that we should realize is that we usually don't measure the amplitude, but that we measure the intensity. So we look for an expression for the intensity, which means that we need the magnitude squared of this equation 31. So let's do that. So we compute the intensity which means that we compute I3, and this is equal to C times N3 epsilon 0 divided by 2. And now the amplitude squared. And if we now substitute equation 30C, namely the third coupled wave equation, then we get C times N3 times epsilon 0 divided by 2, and then many prefactors. Yeah, so we have the square of A2, so we have 2 squared, then the effective nonlinearity squared, omega 3 to the 4th power divided by C to the 4th power and K3 squared. Yeah? And then, of course, still A1 squared, A2 squared, and then, of course, the magnitude squared of what we have in brackets in equation 31. So we have e to the I delta k times L minus 1 divided by I times delta k, and the entire thing squared. Yeah. And now we simplify a little bit all these prefactors. So for example, we write for k basically omega divided by c and things like that. Yeah. So doing all this stuff then leads, after a very quick additional line, this leads to this expression here, 2 times epsilon 0 times the effective nonlinearity squared divided by C and N3, and still A1 squared and A2 squared together with this exponential here. That basically describes what phase mismatch is doing, as we'll see. Yeah? And of course, the interesting part is, of course, this here. And therefore, we start by simplifying it a little bit, trying to get it in a nicer form. So we consider this last term here in equation 32. So consider the last term of equation 32, right? And actually, we start with the numerator. So what we have is here e to the I delta k times L minus 1 squared. And this is by definition the product of this term times its complex conjugate. And if I write down this, then it looks like this. E to the I delta k times L minus 1, and here the complex conjugate. And complex conjugate just means that you need to replace the imaginary unit by minus the imaginary unit. So we copy the first term here. And here we write e to the minus I delta k times L minus 1. Yeah. And we multiply it out. Yeah. And what we get is 1 minus e to the I delta k times L minus e to the minus I delta k times L plus 1. Yeah? And 1 plus 1 is, of course, 2. And now we use Euler's formula. Namely, we write for e to the I delta k times L, we write cosine of the argument plus I times the sinus of this argument. So in this case, this means cosine times this argument. I'm too lazy to write it down. Minus, because we have a minus sign here, sinus of this thing here, and then minus cosine of the argument plus I times the sinus. Minus times minus gives plus. And that's it. And we see, of course, that this imaginary part cancels, as it should be. We definitely expect for an intensity a real number. So if you would get something else, then you would know that there must be a mistake. And if we do this, then we get here 2 times 2 minus 2 times cosine of this argument, and now 1 minus cosine. This is equal to the sine squared. So in this case, then we have 1. No, in this case, I write it down immediately. So we have now 4 times the sine squared of delta k times L divided by 2, right? 1 minus cosine is equal to 2 times the sinus squared of the same argument. So now we can do a small trick. So we expand this expression with L squared, and this then gives L squared times, now this expression, so this factor here that we had here, right? So L squared times this thing here gives, so the magnitude of e to the delta k L minus 1 divided by delta k L squared. So you see why I'm doing this, right? So why I'm expanding here with L squared. What I want to have is in the denominator, what I want to have is I want to have the same argument here and here, right? And you have already seen that we have a sine square here, and if you try to make a guess, then you certainly will not be surprised if we arrive at a sinc function in a minute. Well, in a few seconds, actually. So this gives L squared times 4 times the sinus squared of delta k times L divided by 2. Divided by delta k times L squared, and this we expand with 1 over 4. And then we see the sinc function. So we have L squared times the sinus squared of delta k times L over 2 divided by delta k times L over 2, and this is equal to L squared times the sinc function. That doesn't fit here. Okay, what we get is L squared times the sinc function squared of delta k times L divided by 2. So that's equation 33. Okay, we're almost done. So the hard work has been done. We now substitute this expression into, well, we want to calculate actually I3, right? So we kind of substitute it somewhere here. Well, we also need these expressions, of course. So far, but easy. So now it should work again. Let me see what my monitor here says. Yes, there is something. Okay, so where did we stop? Or where did the audio stop? I guess it is pretty clear. Yeah, so many chat entries now that audio works again. Good. I guess the audio stopped somewhere here. Was nothing complicated what I did, right? I just wrote the intensity as, so I wrote an expression for the intensity in terms of the amplitude, just in order to substitute this thing here over there, and of course the same thing for this here. Good. Yeah, and now we substitute these equations. They get a name actually, 34. So we now substitute these equations 34 into equation 32, yeah, so above there. So 6, 33 and 34 in 32. If I do this, then I get an expression for I3. I3, this is equal to 2 times, and now I copy all these prefactors, epsilon 0 times d effective, omega 3 squared divided by c times n3, and now the expressions for the amplitude squared, so I have 2 times I1 divided by c n1 epsilon 0, and the same thing, the analogous thing for intensity 2, so c times n2 times epsilon 0, right? And then the last term, so which comes from equation 33, so this means L squared times the sinc squared delta K times L divided by 2, right? And this can be a little bit simplified, so all these prefactors consolidated so that we have the effective nonlinearity. So I forgot a square obviously here. So we have omega 3 squared, then we have I1 times I2 And then we have n1 times n2 times n3, c cube, and epsilon 0 and epsilon 0, right? So one of the epsilon zeros cancelled. And of course, we have the important factor, so the essential thing here, where all the physics is, this is this sinc function. Yeah? So everybody knows how a sinc function looks like, but nevertheless, I would show one here. No? So here's the sinc function. Yeah? So this is how this looks like. What does it mean, once again? What it means is, if you propagate for a distance delta k times L, yeah, so if you propagate for a distance such that delta k times L divided by 2 is larger than pi or so, right? Then the intensity drops. Right? So if L is greater than 1 over delta k, then A3 gets out of phase and we start to decrease A3. So we start to feed energy from A3 into A1 and A2. Right? So this is what phase mismatch is doing. So after, so you see that that these 3 waves, they got out of phase. And well, there is one name for that that's pretty unfortunate, actually. This is the length 2 divided by delta k. This is called the coherence length, right? And you know the coherence length probably from coherence theory. The coherence length that I'm talking about has nothing to do with the coherence length in statistical optics. Yeah? So when one speaks about coherence in linear optics, has nothing at all to do. So you get another feeling here that these were not optics people who developed this field, right? So these were some electrical engineers who didn't remember well their courses in physics, particularly in optics. Just what I guess, yeah. Okay, let's write that down, a remark. So the effect of phase mismatch is described by the sinc squared function, by the sinc squared factor. Yeah. When L is greater or becomes greater than 1 over delta k, then A3 gets out of phase with the polarization that creates A3. And the polarization is, of course, created by the other 2 colors. Right? So it gets out of phase with P3, which in turn is created by A1 and A2. Yeah? And what happens then is energy starts to flow back. Yeah, if you make it even longer, this crystal than L, starts to flow back into A1 and A2. Yeah? And the lengths L coherence defined as 2 divided by delta k is called coherence length. And this coherence length has nothing to do with the coherence length in linear optics. It has nothing to do. It has just the same name. It has just the same name then the coherence length in coherence theory or statistical optics but nothing to do with it. Okay, we will come back to this fundamental property of phase mismatch when in one of the next chapters we will discuss phase matching, different methods to achieve phase matching in more detail. So it's a good idea to remember this sinc factor here, or sinc squared factor actually. Okay, so we have a final subchapter in this chapter, namely the Manley-Rowe relations. And so this is chapter 3.5, Manley-Rowe relations. 3.5, Manley-Rowe relations. So far, we said that we look for a simple solution, and we simplified the situation by saying that A1 and A2 are constant, are independent of Z. Now we say that we allow everything, but as you'll see, we still find a simple solution, and these are actually the Manley-Rowe relations. I looked for a while who Manley and Rowe are or were, and finally I found at least one of them, namely I found Manley on Facebook. And so when I looked it up first, he was still alive. So this must have been in 2018 that I looked him up for the first time. And he was just celebrating his 90th birthday with his family. He was still active in September, I found out, right? And took part or noticed the political situation. Here you see this figure here. Unfortunately, he died just a few weeks later, so he died in October 2018. But here you see the paper, which is the basis of the Manley-Rowe relations, and what you see is that fits actually to what I said all the time, namely that the field of nonlinear optics was developed by electrical engineers, or rather the people who started to look into nonlinear optics were electrical engineers who knew the literature of their field. Yeah, so Manley and Rowe, at least this paper here, has nothing to do with nonlinear optics. Yeah? So it describes some general properties of nonlinear elements in electric circuits, right? And if you go on through this paper, right, then you find electric networks with nonlinear elements, such as used in radios and the like. Yeah? And then here at some point, the Manley-Rowe relations, actually, where are they? Yeah, so if you read through the conclusions, then he speaks about general energy relations. If I can read this here correctly, it's very small here. And you will actually see that we do the same thing. Yeah? So these equations or these relations developed for electrical engineering or electrical circuits, they can immediately be transferred to linear optics, from electrical circuits to nonlinear properties or to nonlinear processes in optics. Okay, so with these historic remarks, I always like to know where my field comes, where my own field comes from, what my ancestors are, so to say. Okay, so I didn't find Rowe so far, image or something of, yeah, so the engineers, they don't have the same sense for history as we physicists have, yeah, so it's to find the prominent figures in their field, find it much harder to find them. But if you find some information about Manley, then let me know. So we drop all the simplifications. Yeah? We drop all simplifications. Which means that A1 is a function of Z, A2 is supposed to be a function of Z, and the same thing for A3. Right? And of course, we make no assumption whatsoever about phase matching. Yeah? This means that we allow energy transfer back and forth. So far, when we said that the amplitudes A1 and A2 are constant, then of course there can only be energy transfer from A1 and A2 to A3, strictly speaking. Also, we saw already that there must be energy fed back, because we saw that A3 drops or varies as we change, can go up and down as we increase the propagation distance. Okay, yeah, so this means energy transfer back and forth between omega 1, omega 2, and omega 3 is allowed. I still use this sloppy way of saying it. So I say energy transfer between omega 1, omega 2, and omega 3. You all know what I mean. Yeah? I mean, of course, the waves with these frequencies. So, and now we just look for the intensities. Yeah? So the intensity, we used this expression already, but now we use it for all three fields. The intensity of each field is given by intensity, the I's intensity. This is equal to C times Ni times epsilon 0 divided by 2 times AI star, right? So that's supposed to be equation 40. Well, now if you look back to the coupled wave equations, then you know, of course, that we have here the derivatives. And therefore, it's natural to calculate here the derivative of the intensity with respect to Z. Yeah, so this means that the derivative of this I's intensity is given by, we need of course the product rule because AI and AI star depend on Z. Yeah? So we have then C times Ni epsilon 0 divided by 2. And now we take the derivative of AI, so this means that we just write down AI star and then the derivative of AI with respect to Z plus AI and then the derivative of AI star. Right? And this I can write, of course, in shorthand notation with the complex conjugate. So we have C Ni epsilon 0 divided by 2. And then we have AI star and D and the derivative of AI plus the complex conjugate. Yeah? And from this formula you see already that we have a real number. Yeah? So if we have a complex number and add the complex conjugate, then we get a real number, and this must be the case because this is real. The intensity is a real quantity. The intensity is something that can be measured. Yeah. Okay, so what we do next is that we substitute this so that we choose I equals 1, right? So that we choose this formula for the first wave. And then we substitute this here into, so what you see that we have now this expression here that's in the coupled wave equation. And now if we use here the derivative of A1, then we can substitute this in the first coupled wave equation, which is equation 30a. Yeah? So let's do that. Take 41 for I equals to 1 and use the first coupled wave equation 30a, right? Then you would just substitute here, yeah, okay, so we would do this. And then we have here C times N1. Yeah, so this comes from this part. So this is what I'm going to write down. Epsilon 0 divided by 2. And then we substitute, so the prefactor from the coupled wave equations, 2 times the effective nonlinearity times omega 1 squared divided by K1 and C squared. And then we have this expression that follows. So with the amplitudes, so we have A1 star. This comes from this equation 41 times A3 times A2 star e to the minus I delta k times z plus the complex conjugate. And Frau Hopfe just brought me a cup of tea. Thank you very much. In order to remind us that we should have a small break in a second or so. I just want to complete this line here, and then we make 3 minutes or so of break. So now we replace k with omega divided by c, and what we get is, so a few things cancel here, of course. So this here cancels. What else cancels? The factor 2 here also cancels. But that's it. So what we get here is n1 epsilon 0 times the effective nonlinearity omega 1 squared times c. Yeah, this we get from k1. Yeah? And then we have n1 omega 1 divided by c. Right? And now there's a massacre here. So we have n1 cancels, and what else cancels? Of course, this omega 1 like this, right? But the rest remains. So we have I times A1 star, A3, A2 star, e to the minus I delta k times z plus the complex conjugate. Yeah, and now what you see is, actually for the first time probably here in this course, so what you see that we have now I here, right? So when we have such an expression without the imaginary unit and we take the complex conjugate, then we get the real part. And now we have I here. This means that we now get the imaginary part. Yeah? You can also calculate this by doing an example, right? Take a generic complex number and just do this calculation. You will find the same fact. So what this then means is that the derivative of the intensity of the first intensity is equal to minus 2 times epsilon 0 times the effective nonlinearity omega 1 times the imaginary part of A3 times A1 star, A2 star. And the phase mismatch or phase matching factor here. So that's equation 42. Yeah? So, and with this, we make a small break. I get my tea. And I hope you also find a quick cup of tea so that we clear a little bit our brains. Well, don't clear it. And so that we start fresh in a few minutes. I may use the time to tell you a little bit of nonsense. I actually planned to put a Christmas tree here, and I ordered one, but it is not delivered. Next Monday, I hope there is one here. And perhaps we play a Christmas song then next Monday. So if you have any suggestions, let me know. Of course, if you prefer a coffee, then you can also have a coffee. In particular, if you have the feeling that's a little bit boring here and that you get tired, then coffee is perhaps better. So everybody has now a cup of coffee also, some chocolate. Chocolate also would have be a good idea. Okay, yeah. So we got an expression for how the intensity A1, the intensity I1 behaves, how it changes with distance. And now if you look at this formula, if you look at our formula here, 41, then you see that we could have done the same thing for the second wave and for the third wave, and we would get very similar equations. And of course, I did this once. And I don't want to repeat everything here. I just want to write it down for the second and third wave. So in the same way we find that the slope of the second wave is given by, well, exactly the same expression, just with the indices changed accordingly. So we have A3 times A1 star, A2 star, e to the minus I delta k times z, right? And similarly for the third wave. So we find di3 over dz is equal, only one change here, namely a plus sign. 2 times epsilon 0 times the effective nonlinearity times omega 3 times the imaginary part of A3 times A1 star, A2 star, e to the minus I delta k times z. Oh. So delta k so like this. Yeah? And yeah. Okay, now we know how each of these intensities develops. Yeah? And we may first have a quick look at the fact that we have a plus sign and a minus sign here and here. Well, if you think about it, then it makes a lot of sense that this intensity I3 has a different sign, has the opposite sign of I1 and I2, right? Because we know already that if we create a photon at the sum frequency, then we need to destroy two of the two other frequencies. Yeah? Okay, let's write this down. 2 remarks. The first one I made just, namely di1 over dz and di2 over dz have the same sign and di3 over dz the opposite sign. Yeah, this makes sense. in order to create one photon at the some frequency, a photon of each I1 and I2 must be destroyed or sacrificed. Yeah, destroyed. Yeah. Well, I said destroyed, but of course energy can also flow in the other direction, right? So we can destroy one photon at the some frequency and produce two at the other two waves. But this is actually included here because A1, A2, and A3 are complex numbers, so that I wrote here a minus sign, here a minus sign, and here a plus sign. Yeah, so this is just depends on on nomenclature, basically on how we set it up. Yeah. So it should be noticed. Yeah. So it should be kept in mind that our equations also describe the opposite case, also describe the opposite case. Yeah. Remember, A1, A2, and A3 are complex numbers. Okay, but this is still not the Manley-Rowe relations, but we are almost there. What we do next is that we sum these equations up, right? So that we take the sum of the equations 42, 43, and 44. And why are we doing this? Well, as we indicated all the time, so we said one photon is generated and two are destroyed, or one is destroyed and two are generated, which implies in some way that energy is conserved. Right? And we now want to see how this works. Yeah? So these equations 42 to 44 imply energy conservation. Yeah. This can be seen by inspecting the total intensity, namely the sum of all intensities, the total intensity I equal to I1 plus I2 plus I3. And then we take the derivative of the total intensity. So we take the derivative of I, which is of course the derivative of the first intensity plus the derivative of the second intensity plus the derivative of the third intensity. And now we substitute our equations 42 to 44. So this is just what we calculated above here. So these three derivatives of the intensities. And what we get is, so the nice thing is, of course, that we have the same, that this factor here you find in each of these four equations, and actually you also find this factor here in all the equations. The only difference is actually between these different equations is omega 1 and omega 2 and omega 3, and of course the sign here. Right? And therefore, we can write that this is minus 2 times epsilon 0 times the effective nonlinearity, and then omega 1 plus omega 2 minus omega 3. Yeah? And then this imaginary thing over there. Yeah? What does it tell us? Any idea? Question to the audience? Somewhere around the world? Nobody? Simple question actually. Well, omega 1 plus omega 2 is equal to omega 3, which means that this here is equal to 0. Right? And this is just what we expect. We expect that the intensity, the total intensity, doesn't change. If there's no absorption, why should it change? Right? So what follows is that the derivative of the intensity is equal to 0, or in other words, the intensity is constant, which is no surprise. This is no surprise because we derived the coupled wave equations for non-absorbing, for lossless media. Yeah? Because we derived the coupled, I want to introduce at some point an abbreviation. So the coupled wave equations for lossless media. Yeah? But actually what we also can do is to write this trivial thing in a little bit different way. What we can do is that we divide these equations 42 to 44 through omega I. Yeah, so that I have this omega I on the other side, right, like this here. Right? And then you see that this right-hand side is basically identical, disregarding the sign. Right? So this would be the next thing that I'm going to do. So next, we divide 42 to 44 by omega I. Right? And what I find then is that the change, the slope of the intensity normalized to its frequency, that they are equal disregarding a sign. Yeah, so I1 and I2, they are indeed equal, but here we get a minus sign for I3. Yeah? And these are the Manley-Rowe relations. Yeah, so you see, pretty trivial thing. And in an electric circuit, this should be the case. Yeah? So if no energy is dissipated there, Kind of interesting that it took until a paper from the 50s, as a Manley and Rowe, they were working for the Bell Labs, one of the very prominent research institutes, industry research institutes at that time. And after the economists took over the management of the Bell company, the Bell Labs disappeared from the scene, more or less. Okay, so this is equation 45. So these are the Manley-Rowe relations. Yeah, we can also write them pairwise. But it's perhaps not so important. But actually, writing so these Manley-Rowe relations, they have actually a nice interpretation in the photon picture, because you see that I divided by omega 1, that this is proportional to the photon numbers, right? Same thing here and here. Right? And so this literally tells you what we said all the time already, namely that if you create one photon at omega 3, you need to destroy two, so each, one photon in omega 2 and one photon in omega 1. Right? So it has a nice explanation in the photon picture. Yeah, so you probably wouldn't easily interpret the situation in an electric circuit in this way. But of course, in optics, this is a natural explanation. So the interpretation would be the rate at which I speak of the rate. Yeah, so rate we usually mean in the temporal domain. I mean it in the spatial domain here, actually. So the rate at which photons at frequency omega 1 are created is equal to the rate at which photons at frequency omega 2 are created, and this is equal to the rate at which photons at the frequency omega 3 are destroyed. Yep. Once again, the assumption is that we have lossless media. Yep. Once again, we assumed lossless media. Okay, so far so good. We have now looked at the two extremes, more or less. Yeah? So in the one extreme was that we assumed that A1 and A2 are constant, because A3 is so weak that hardly any photons are taken from A1 and A2. And then we looked at the very general case but we only looked at the intensity and actually at the total intensity, and then we found, also the situation was the most general one, we found another, well, trivial solution. Mr. Rowe might forgive me if I say this in this way. In the next chapter, we will look at less trivial solutions. We will look at non-trivial solutions of the coupled wave equations. I wouldn't say that the previous ones were really trivial, because the insight that we got for phase matching and actually also the Manley-Rowe relations, they are profound. And actually, the one for phase matching will have another look at that in a future chapter. But now we want to look at a situation where we actually assume that that one of the fields is still strong, so such that we can neglect its spatial variation, such that the derivative of that strong field is in a very good approximation 0. So we will use A2. So we will assume that A2 is very strong, but we assume that A1 is also weak, and of course A3 will be generated in this crystal, and therefore it will also be weak, right? So this means that only 2 of the amplitudes depend on Z. And you might say, well, this is a fairly artificial situation. Well, actually it's not. Think about the following situation. You have some infrared field, but you don't have a good detector to detect it. Because in order to detect infrared photon, you need a detector that has a band gap, solid state detector that has a band gap that's very low, right? And so you need to cool it and all these things in order to get rid of thermal noise and blah, 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 right? So you might decide that you convert this infrared photon into a visible photon for which you have a good detector, right? And of course, the only way to do this is nonlinear optics. So, and we'll look at this situation in the next chapter, which has the headline, Non-Trivial Solutions of the Coupled Wave Equations. Chapter 4, Non-Trivial Solutions of the coupled wave equations. So, and what we start with is the so-called undepleted pump approximation. So for one, the undepleted pump approximation. Good. So, yeah. We assume that the incident waves A1 and A2 are very weak, and strong respectively. Yeah? And what this means is that A2 will be independent of Z. Yeah? Will be independent of Z. Of course, I need the index here still. Yeah? However, now if A1 is very weak, then this means if I destroy a few photons there, this will have a noticeable effect on A1, right? So this means that A1 and A3 depend on Z. Yeah? And real world application. Suppose you want to measure or detect rather. You want to detect infrared photons but find it difficult, but you have difficulties to find a detector, to find a noise, a good detector, yeah. A good, say, low noise detector. Detecting infrared photons, this is not so easy. The more difficult, the farther you're in the infrared. Yeah? Then the solution can be to convert the infrared photons into visible photons. By some frequency generation. Yeah. Okay. So with this situation, it is clear that our three coupled wave equations are actually just two coupled wave equations. Yeah. So if dA2 over dz is equal to 0, then we just have dA1 over dz is equal, and now in order to avoid all these constants, I just write k1. Yeah, so k1 includes, of course, then A2, but I still have, of course, A3, and of course the phase mismatch factor. With k1 is equal to I times 2 times the effective nonlinearity omega 1 squared divided by k1 c squared A2 star. So that's equation 1 in this chapter. And a similar equation a similar equation for A3. This is then K3 times A1 e to the plus I delta K times Z. And we would define a constant K2, no K3 of course. Yeah. And this would be equation 2. Yeah. So now we want to solve this. Yeah. And so we want to look first at the simple situation, namely where we have perfect phase matching. So some frequency generation for perfect phase matching would be the next subchapter. That's for 2. Some frequency generation in the undepleted pump approximation for perfect phase matching. So the situation is quite simple. So what we do is that we take the derivative of this equation 1. We take the derivative of this equation 1, and then we'll have, of course, the second derivative here, but we'll have the first derivative here, and then we can substitute equation 2 into equation 1. Yeah? So very straightforward what we are going to do. So we take the derivative of 1, of course, with delta k equal to 0, right? So we said perfect phase matching. And then we have, as I said, the second derivative of A1. This is equal to K1 times the first derivative of A3. And we use now we use equation 2 to eliminate this first derivative in equation 3. And what we get is now the second derivative of A1 with respect to Z, and this is equal to K1 times K3 times A1. And we introduce another abbreviation, namely kappa squared actually, times A1. And now if you look which sign kappa has, then you find that it's positive. Yeah, so kappa squared is equal to minus K1 times K3. And you find that in K1 and K3, you have this imaginary unit here. Imaginary unit times imaginary unit gives, of course, minus 1 together with this minus sign. It will give a positive value. Right, so we can write that down. So this is equal to plus 4 times the effective nonlinearity squared, omega 1 squared, omega 3 squared divided by K1 K1 and K3 times speed of light to the 4th power, and then we have A2 squared, right? So this means that kappa squared is positive. Right, so let's call this equation here 4 and this equation here 4a. Yeah? Everybody has seen this differential equation already. Yeah? So such a differential equation, everybody knows, I guess. Right? So what we have is second order differential equation, and here's zeroth order on the other side, and this is an oscillation, right? And kind of the oscillation frequency, this is this kappa squared. Good, yep. So it is immediately clear what the solution is. It's a linear combination of a sine and a cosine. Yeah? And we need to find then the coefficients of these of the sine and the cosine. So the general solution to equation 4 is A1 of z is equal to b times the cosine of kappa times z plus c times the sine of kappa times z. Right? And of course, these coefficients kappa, they need to be determined by the initial conditions. Yeah? But before we do that, we actually make the remark that once we know A1, we know, of course, also A3. Right? So if you look back here at this equation 2, once we know A1, and we know it in principle, then actually the other way around. Right? So once we know A1, we can calculate A3 with equation 1. Good. Let's write that down. Once we know A1 of z, we know via equation, we can also use equation 3, of course. Yeah. But equation 3 is wrong, isn't it? No. Yes. What did I do? Yeah, it's fine. Yeah, of course. We know via equation 1 also A3 of z, right? And if we do this, then we get A3 of z is equal to 1 over K1, and then here the derivative of A1 over z, and therefore we have minus b times kappa divided by K1 plus c times kappa divided by K1 times, oh, I forgot the sign here. Yeah. So sinus of kappa times z plus c times kappa divided by K1 times the cosine of kappa times z. So this is equation 6. And the next point would be, of course, to determine these coefficients b and c. Yeah, so we use the initial conditions to determine b and c. Yep. So, what would you choose as initial conditions? Most of the time this is straightforward, and also here it is straightforward, because what you most of the time will have, and actually this is how we discussed this problem, the assumption, the tacit assumption was that we have two input fields, namely A1 and A2. A2 is strong, but never mind. And A3 is equal to 0 at the entrance phase of the crystal. So if you put the entrance phase of the crystal to Z equals 0, then this would be an initial condition. Yeah? And this is what we are going to use. So this is kind of, natural initial conditions. Yeah? So what we assume, that there are no omega-3 photons at the entrance phase of the nonlinear crystal. Yeah? Which means at Z equal to 0. Right? And this means that A3 at the position Z equal to 0 is 0. Right? And this means immediately that C is equal to 0 because the cosine at the position Z equals 0 is 1. Yeah? So we use C equal to 0 in this equation 5. And then we find the coefficients, the other coefficient, namely B. Yeah? So what we do is, and then we would stop for today, we use C equal to 0 in 5. And what follows is that B is equal to A1 at the position Z equals to 0. Right? And then we would write that A1 of Z is equal to A1 at the position 0 times the cosine of kappa times Z, and A3 of Z is equal to minus A1 of 0 times kappa divided by K1 times the sinus of kappa times Z. And that's equation 7 and 8. Yeah? And the next thing would be that we discuss the physics of what we found here mathematically. But this we'll do next Monday. So have a good week and see you next Monday. Thank you.